Ben.
Thank you, David. So I'm not going to attempt to answer all of your questions because there's not time. In particular, I'm not going to attempt to discuss how reactors are supposed to work. Reactors are supposed to do a certain thing, and they're supposed to produce power in a certain way, and they're supposed to regulate that power in certain ways, and they're supposed to not blow up. And that's a little irrelevant now, so I'm just going to leave it aside in the case of Fukushima. The thing that's relevant now is that these reactors are leaking radioactivity. Radioactivity is a very scary thing for many people. And I think that's what's important in the near term. That's what's important for the people of Japan. And many people are concerned about whether or not it's important for us. So the main thing I want to talk about is what is the radioactivity that's coming out of these reactors? Why is it in there to begin with? How does it affect you if it gets to you? And how does it get to you? How does it get out? And we'll talk about the implications of some of that. So this is I recognize there's a bunch of actual physicists in the audience. This is not a talk for physicists. This is a talk for the general public. Physicists have their own ways of figuring out what a microsievert is. This is for the rest of you. So to understand where radioactivity is going, we have to look at different radioactive elements. And different radioactive elements are going to behave different ways depending on their chemical properties. So this should be familiar to you because this is the table used by the California Department of Education. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, and so on, all the way up to uranium, plutonium. And some of the elements that you'll be hearing about in the news on a regular basis are things like iodine, cesium, tritium. And the reason you're hearing about them is not that iodine is inherently dangerous. You probably dealt with iodine in your high school chemistry labs. But there are isotopes of iodine that behave just like regular iodine, except that they're radioactive. Likewise for hydrogen. There's an isotope of hydrogen which is radioactive and fairly hazardous. And so is cesium. But in terms of understanding what they do, that's a job for chemistry. And so we'll be going back and forth between the nuclear side and the chemical side. For the nuclear side, like why is some hydrogen safe and other hydrogen dangerous? Well, the thing that defines it as hydrogen is that it has just one proton and therefore one electron. That's what gives it the chemistry that you associate with hydrogen. That's what makes it able to go into H2O, this kind of thing. But that doesn't define the number of neutrons. You can take that one proton and have it all by itself, in which case it's the hydrogen that you mostly know and love. Or you can add a neutron to it, or you can add two neutrons to it, and then it becomes radioactive. That doesn't change the chemistry at all. It still behaves like hydrogen. So in order to understand the radioactive side of it, we have to go to a different graph where we have a place to put the neutron number. So what I'm going to show you now is we're going to unwrap this and just list the elements in order on the vertical axis. So here's hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen. Stack them up. There's no periodicness about this. We're just going to list them in order. And that's the number of protons. And in this axis, we're going to represent the number of neutrons. So hydrogen, normal hydrogen, H1, is just one proton all by itself. H2 is what happens when you add a neutron. So hydrogen 2 is also known as deuterium. Both of these are drawn in black because they're stable. They're safe. They're not radioactive elements. If you add that third neutron, we change color to green, representing radioactivity. Tritium is H3. It's got two neutrons and one proton, adding up to 3. That's what this number is the total. It's a heavy isotope of hydrogen. It is radioactive. The same sort of pattern is true of everything in the periodic table. All of these nice, familiar, happy elements like helium, lithium, beryllium have the safe, familiar elements, the safe, familiar isotopes that you've seen before. But if you add a couple of neutrons to them, you get this short-lived radioactive stuff that's going to emit particles as it decays. It also happens if you remove neutrons from them, you get other radioactive particles, but that's almost totally irrelevant here. Those are very rare in nature. But here's this line of stability. We're going to zoom in on this in a couple of different ways. One thing to look at is where do things decay? When tritium decays, this is H3, that tritium, it goes to helium-3. It just wants to change a proton into a neutron. It changes a neutron into a proton. Because it has, remember, all this stuff has too many neutrons. It's all neutron-rich. I'm going to zoom out again. So here's that same chart. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, so on. Vanadium, and so on. And uranium will be up there somewhere. And here's that vast universe of either short-lived radioactive or less short-lived radioactive. And then here's this nice line of stable stuff. So anything that you could possibly manufacture over here is going to be radioactive in some way. And if you make it, it's going to decay by going hop, 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 hop until it gets to something stable. This is the majority of the radiation you're hearing about already at the Fukushima reactor accident. It may not be the majority of the radiation that you hear about in the future, depending on how fires and things go. I'm going to zoom out one more time to show you the whole table. So this is practically every nuclide we've ever seen in nature or made in a lab, ranging from hydrogen way down here in the corner. There's hydrogen-2, there's deuterium, tritium, and you stack them up all the way here until you get to lead. So that's the valley of stability. Those are all the stable isotopes, and that's the vast majority of what you experience in daily life. This black line running up the middle of this thing. If you have lots of protons, you generally have to have lots of neutrons. The relationship's not quite 1-to-1. It's not 1 neutron per proton. Over here, it's more like 1.2. Excuse me. Let's see, look up here. There's something funny going on up here. This is a very interesting region of the chart, because I said this is hydrogen through lead, maybe bismuth, depending how you're counting. There's a gap, nothing stable, and then suddenly there's uranium, thorium, plutonium, the fuel for reactors. This is stuff that's stable enough that nature has given us big piles of it. There is a lot of uranium on Earth. It's actually not uncommon at all. And it's been sitting around since the birth of the planet, 4 billion years ago. I actually have a bit of it here. Here it is. This is a bit of uranium ore, very low level. This is, I think, a kilobecquerel or so. I'll explain what that unit is in a minute, and that'll explain why I'm not afraid of it in this case. So what you do when you're building a reactor is you dig up a bunch of uranium, you put it in a box, and there's some complications. It's the simple. And then you try to make it fission, which means you hit it with neutrons in brushing every possible detail under the rug. Fissioning a uranium atom is splitting it in half. You take this one giant nucleus, you kind of make it go bleb in the middle, and it splits into 2 big nuclei. Not of exactly the same size. There's usually a bigger one and a smaller one. And there's often a couple of neutrons that pop out too. But for the most part, you're dividing the protons and the neutrons in half, and you're making two things with half the neutrons and half the protons. But look, if you divide these numbers in half, I'm following a straight line down here, you don't end up on the stable line. Fission does not produce stable isotopes immediately. It produces very neutron-rich isotopes, often very, very neutron. Some of the richest neutron things you can make outside of very specialized circumstances. So when you're running a fission reactor, this is what you want to do. This is where you get all your power, and this is where you get a bunch of radioactive waste. It doesn't stay there forever, because remember, this stuff's all unstable, and unstable means it decays, which means it moves that way, moves back to the line of stability over various time scales, sometimes seconds, sometimes years, sometimes thousands of years. And once those nuclei have reached the line of stability, they're stable. Stable nuclei, just like the ones you're used to. Indeed, most of the nuclei that you're made of, let me correct that. Most of the nuclei in your body or in your environment that are heavier than iron, at one point in their history, were some horrible radioactive thing on this side of the chart. All of the gold in your wedding ring was, 4 billion years ago, was a pile of radioactive iridium, and then it decayed into gold. So these products are really perfectly safe once they've decayed. The problem is getting them there. So that's the reactor's job. That's where you get all the power from. It's where you get most of the power from. About 95% of your power comes from that fission process, and then another 5% comes from the final walking back slowly to the line of stable isotopes. The other thing to note, remember that this axis of the chart was hydrogen, helium, lithium, and so on, up to uranium up here. So when I draw these blobs, that spans a whole lot of elements. That's everything, almost everything from krypton up to what, gadolinium or something. So there's a vast swath of the periodic table represented chemically here. So if you want to, control these things chemically, you have to know what they are. Well, they're everything. There's all kinds of materials in here. So that's some of the radioactivity of a reactor, not all of it. The other thing you have is that uranium and plutonium and whatever is sitting there in your reactor core, the stuff that you wanted to fission doesn't all fission. Sometimes the uranium atom will capture a nucleus and not fission, which changes it from uranium into something else, which then decays, and you can capture a neutron out of that. And so there's a bunch of neutron shuffling around that happens up here. We call it neutron capture on fuel. I don't know what it's called technically. And you end up with kind of a smear of stuff in the vicinity of uranium, and that piles up in your reactor. That's mostly what we call minor actinides. Also radioactive, because that's all, it's not those couple of nice black stable dots in the uranium area. It's all the stuff around it, because the neutrons shuffled things from place to place. The third way of getting radioactivity in a reactor context is that you have all these neutrons flying around. They don't just hit the uranium, they also hit the steel and the water and the nitrogen and everything else. So neutron capture on other materials can make a bunch of induced radioactivity. And if you're actually working in a nuclear power plant or working in a radiation environment generally, this is what gives you most of your headaches, because this is kind of on things that you're not normally being very far away from. If your pump is radioactive, if your valves are radioactive, it's because of stuff like this, and that takes a lot of work. But it's not most of the radioactivity. Most of the radioactivity that's actually in the fuel is in this stuff up here. And that radioactivity is releasing energy. We want it to release energy because we want power from this fission process. But let's look at how that energy is released and understand how it's harmful.